Good morning, students. So today we are going to see about what are the other memory devices are available in subject. So here non-volatile storage is offered by RAM and some other flash technologies like example flash remaining intact even when the power supply is removed. So volatile storage is offered by static RAM, random access memory, that is SRAM. Data can be written into readout from the SRAM but is lost once the power is removed. And application of memory. The memory devices are often used in a computer systems. The central processing unit often makes the use of buses, a bunch of wires in parallel to access external memory devices. So the address bus is used to specify the memory location. So that is being read or written, and data bus conveys the data to and from that location. So more than one memory device will often be connected to the same data bus. And what are the bus connection? What does mean by bus contention? And in this slide shows the bus contention. In this case, if the output from data pins one memory was 0, and if the output from the corresponding data pin of another memory A is 1, and the data on the line of data bus would be invalid. So how do we arrange for the data from multiple memories to be connected to the some bus wires? And this slide shows the tri-state buffer, and here we have a bus line and a symbol. So output enable OE which is equal to 0 and OE which is equal to 1, and output OE which is equal to 0 means output disable, and the functional analogy means OE which is equal to 1 and OE which is equal to 0. That is, we have a bus line and we have a open switch means open circuit, and a close means closed circuit means a closed circuit. And in this slide shows the control signals, and we have already seen the memory device have an additional control input output enabled that determines whether the output buffers are enabled. So other control inputs are also provided. So write enable determines whether the data is written or read, clearly not needed on a ROM. Chip select determine if it is a chip is activated. So note that these signals can be active low depending upon the particular device. And the sliding state assignment, current state and next state, ABC 000 up to 110. So we have a next state 001 to 000, unused state 010, 101 and 111. We have only 4 states up to 4 by means of 100 in the case of 8421 codes. And by inspection we have seen that we can use any other flip-flops output as the wanted output. Plot K-map, draw the K-map to determine the next state logic for flip-flop A. We have a 3 variable K-map for finding the next state of logic circuits for this corresponding logic expression. So here also the state assignment by inspection we can see that for flip-flop B. So the previous slide shows the flip-flop A, and this one shows the flip-flop B and flip-flop C, and this is for also ABC. We have input and next state and previous state. Next state we have from 00 to 100, and unused state is 010, 101 and 111, and next state will be a 001 and 111 and 110 and 100. For this inspection we can see that for flip-flop B, so this is DB which is equal to A for flip-flop C, and DC which is equal to B. So one hot state encoding, so this is a shift register design style where only flip-flop at a time holds at 1, and consequently we have one flip-flop per state compared with the log2m for sequential assignment. So however can result in simple fast state machines. So outputs are generated by ORing together appropriate flip-flops outputs. And one hot example, so we'll return to traffic signal example which recall has 4 states, and for one hot we need one flip-flop for each state, so that is 4 in this case, and the flip-flops are connected to form a shift register as in the previous shift register example. However, in one hot one flip-flop hold at 1 anytime, and we can see write down the states transition table as shown in follows. So this is we will return to the traffic signal example. We have 4 states, that is red, green and ampere, and ready state and no state, and green signal state and ampere state. So this is also for the same state diagram and current state and next state. Red RAGA, R A bar, R bar A bar, G bar A bar, and unused states are lots. That is 1 0 0 0 0 1 0 0 0 0 1 0 0 0 1 0 and 0 0 0 1, and the next state will be a 0 1 0 0 0 0 1 0 and 0 0 0 1 and 1 0 0 0. So because of this shift register configuration and also from this state table we can see that DA which is equal to green, DG which is equal to RA, and DRA which is equal to R, DRA which is equal to A. To generate RA and G outputs, we do the following ORing operation. R which is equal to R plus RA, and A which is equal to RA plus A, and G which is equal to G. And this block diagram, this circuit diagram shows the one hot example for the traffic signals. Here in the previous slide we discussed DA which is equal to G and DG which is equal to RA, and DRA which is equal to R and DR which is equal to A. So here the ORing operation we perform and we get R which is equal to R plus RA, and A which is equal to RA plus A, and G which is equal to G. We have 4 flip-flops and D flip-flops, and D is the input and Q bar is the input. First flip-flop input is D, and output will be R, and second output will be RA, and third output will be G, and fourth output will be A. So again the clock will be given to the each D flip-flop, so that output should be written R which is equal to R plus RA, and A which is equal to RA plus A, and G which is equal to G. So this is a circuit diagram for that particular controls in the traffic signal. So here we have a OR operation and OR operation using flip-flops, and that is D flip-flops.